Hello, in this lecture we're going to talk about energy and intensity in waves. This is part 4 in the series of talking about everything related to waves. Now this is a poor depiction nonetheless, of a ripple wave produced when you throw a pebble down here in the middle of a pond, okay? Or anywhere on the pond. If you throw a pebble, we can see waves circularly spreading out, like so. The waves spread out from the center, which is the source, and we call that this pebble is the main source behind this wave, behind the cause of this oscillation, which results in a wave. Okay, and the wave propagates outwards circularly, as shown, right? And we can see that ripple waves are actually transverse waves because the propagation is perpendicular to the particles oscillation or molecule oscillations that is causing the wave. Okay. Now, if you really talk about surface waves of water, then the discussion gets more complicated. However, in a very simple picture, this kind of wave is also a transverse wave. Okay. Now, as it spreads out, it gets farther and farther away from the source. So, what is the point of the source? What does it do? The source puts energy into the system, which is the water body, and then when you put some energy in, you make the particles or the water molecules oscillate, causing a wave, and these waves cause crests. Or crests are, as we know, if you look at a wave diagram, the highest points of the waves, the amplitudes of the waves. So these crests are also called wave fronts, and these crests carry energy away from the source, alright, like this, as they propagate from here, from their origin to the outer parts of the wave. And it's only normal because if you get far, it's only normal to assume, and it's only logical to assume that as you get farther away from a source causing a vibration or oscillation that results in a wave, the lesser energy the wave must have. You can think of it very simply as a light bulb. If you have a light bulb that's glowing, that's giving out light in your room, and you're standing here, you feel that the light is very bright. When you move away from that source of light, the light bulb, you automatically are in a more darker state. Okay, the light doesn't reach you well enough at all this in this larger distance. This leads us to the idea of intensity. The fact that energy gets smaller as you propagate, as the wave propagates farther away from the source over a particular area, is help us define intensity. And intensity is defined as I equal P over A, where P is the power and A is the area over which the wave spreads. Power, we know, is energy over time. So intensity is basically energy per unit time for surface area. Alright, and energy and the area over which the wave spreads could be, for a ripple wave, it's a circle. So the area, because it spreads out circularly, right? And so the area would be then pi r squared for a ripple wave. But it may be different for the light source. For usually wave spreads out spherically from light source like the sun, the moon, or even light bulbs. And spherically meaning the area would then be 4 pi r squared, the surface area of a sphere. The SI unit for intensity is watt per meter squared, because the SI unit for power is watt, while SI unit for area is meter squared. Now let's look at an example that clarifies the idea of intensity. Consider an LED bulb which has a power of 72 milliwatts. Milli means you, to get the SI unit watts, to get power in watts, you simply divide 72 milliwatts by 1000, and you will get the power in watts, which is let's just keep it as 72 over 1000 watts. Alright? Now we want to find out intensity at a distance of 5 centimeters away from this LED bulb. LED bulb is now the source of the light wave coming that you are seeing, and then we know that the formula for intensity, we just learned it to be I equals power over area. We know the power, but do we know the area? Well, we do know the fact that light spreads out spherically as discussed here, and the area would be the surface area of a sphere. So for power we write down 72 over 1000, and for area we write down 4 pi r square. What is the distance? What is the r? What is r? Well, r is the radius of a sphere, and for a spherical wave from a source at this point to where you're standing 5 centimeters away, r is 5 centimeters, or 5 over 100 meters. Alright, so 4 pi 5 over 100 squared. Alright, this will give you the intensity at 5 centimeters, and we get the intensity, let's just call it I1, to be 2.29 watt per meter squared. Alright, pretty simple. Now there is a second part to this question. It simply asks, what is the intensity at r equals 10 centimeters? We do the similar thing, let's just call it I2 for now, and the power is still the same because the source hasn't changed, so power is still 72 over 1000 watts over 4 pi r squared. Now r has changed, you have moved farther 5 centimeters away, so 10 over 100 squared. This gives you an intensity of 0.57 watt per meter squared. Alright, this is the intensity at a distance of 10 centimeters away from the light source. Now let's compare what I1 and I2 is. So think about this one. You were standing 5 centimeters away and you calculated I1. Now you moved twice the distance away. You moved to 10 centimeters and you calculated I2. So if this formula were true, if indeed intensity is for this light bulb, for this LED bulb or any bulb spreading out spherically, is indeed power over 4 pi r squared, that would mean if the power stayed constant and 4 pi is a constant, then if r changed, if you double r, you would decrease I by 4 times, right? Because r is squared, so if you double r, then you would decrease I by 4 times. Let's check if that's correct. Alright, so to do that, we just take the ratio of I1 over I2. What was I1? I1 was 2.29. What was I2? I2 was 0.57. When you divide that, you get I1 over I2 to be 4, meaning I1 is actually 4 times that of I2, or if it makes more sense this way, I2 is 1/4 of I1. So indeed the intensity decreased by a factor of 4 when you moved a distance 2 times away from your original distance. Okay, I hope this discussion on intensity and energy in waves makes some sense. Thank you very much.